Here we go. Good evening. All right, let's go ahead and let me go ahead and start this week's lecture. So I'll go to Jupyter Notebook. All right, so as I've told you a few times, we are now finished with the part of the course that has to do with Introduction to Python and NumPy. And we're well into the part of the course that has to do with the mathematics of sound and of speech production. 2 lectures ago, I told you that all sound is made up of sine waves. And last lecture, I told you that speech, in particular, is made up of a glottal, a vocal folds. Your vocal folds close once every 10 to 20, once every 5 to 10 milliseconds. And that closure causes an impulse of pressure, which excites the resonant frequencies of the vocal tract. And so now we come back around to sine waves. Next lecture, we're going to analyze real speech in the way that last time we analyzed synthetic speech. And in the lecture after that, we will synthesize real speech using audio from our analysis of real speech. But in order to do that, we need to know how to take a real audio waveform and break it down into sine waves and cosines. And so this week, I want to teach you about something called the Fourier transform. The Fourier transform was invented by Joseph Fourier in the 1860s in order to represent the flow of heat. Believe it or not, this concept was designed to represent the flow of heat. It's turned out to be very useful for the analysis of any linear system. So it turns out that any linear time invariant system, for example, any system that's made up of echoes, takes an input sine wave and reproduces at its output a sine wave at the same frequency, but shifted in phase and possibly scaled by some amplitude. And so because sine waves are special for linear time invariant systems, therefore sine waves are special for acoustic systems, and therefore it's useful to be able to analyze any audio signal in terms of sine waves. So what I want to do today is to teach you about analyzing audio signals in terms of sine waves. We're going to start out actually analyzing audio signals in terms of cosines. And the way that the Fourier transform works, the Fourier transform assumes that our sound is made up of a sum of cosines. If our sound is made up of a bunch of cosines, then how do we get those cosines back again? It turns out that the way that we get a cosine back again is by multiplying it by the same cosine and then adding over their samples. And so this formula that I'm showing in the center is really the critical formula. This is really the main formula for Fourier transform analysis. If you have a frequency, if you have an input cosine, which is at some frequency m, and you multiply it by a cosine at some other frequency k, and then add over one complete period, then the sum is equal to 0. For example, if k is equal to 3 and m is equal to 4, if I add over one complete period, then the sum is equal to 0. So I want to show you how that works. Let me import NumPy. And then let me go ahead and take k is equal to 3 and m is equal to 4. And I'll take a total of 20 samples just in order to have something that's easy to plot. Small n will be the numbers from 0 to 19, right? And then I'll create a cosine at the frequency k and a cosine at the frequency m. And then I will multiply those two and add together the result. right? So when I add together the result and multiply those two and add together the result, the total will be basically 0. It will be 10 times to the negative 15th. And then I can plot in subplot 0, I'll plot x. In subplot 1, I'll plot y. In subplot 2, I'll plot the product of those two cosines. So let's plot that. So here in subplot, you can see that in subplot 0, I have a cosine that has 3 complete periods. 1, 2, 3. In the second plot, I have a cosine that has 4 complete periods. 1, 2, 3, 4. And in the bottom, I have the product. I have this cosine multiplied by this cosine. So you can see that a positive number times a positive number is a positive number. A positive number times a positive number is a positive number. A negative number times a negative number is a positive number. And so on. So we have some positive numbers, some negative numbers. Here's a bunch of positive, here's a bunch of negative. But if you look, you can see that the negative numbers exactly match the positive numbers, right? That's because what's happening in this part of the period is exactly the opposite of what's happening in this part of the period. And so when we multiply this cosine times this cosine, the product is something that has an average value of 0. And so when we add up all of those samples, the total value is 1.8 times 10 to the minus 15. The average of all of these samples is actually 0. Each individual sample is large, but because these samples exactly cancel out these samples, the total is 0. All right, so this is called the principle of orthogonality. Orthogonality means perpendicular. Let's look it up on Wikipedia. Let me go to Wikipedia. And let's look up what orthogonal means. Orthogonal means perpendicular, like this. AB is perpendicular to BC, right? These two things are orthogonal, which means that the angle between them is 90 degrees, right? And the cosine of 90 degrees is 0. So orthogonal means that they're perpendicular. It means that if we take the dot product of this vector, dot product with this vector, we get 0. They point in completely independent directions, completely unrelated. And what we're seeing here is that this generalization of that, if we multiply this cosine multiplied by this cosine, and then average across all of the samples, we discover that the average is 0. And that turns out to be useful because there's one exception. There's just one exception when k is equal to m. If I take k equals 3 and also m equals 3, right? If k is equal to m, let's go back and look at this magic formula. Here's the magic formula. This is the most important formula. If k is not equal to m, multiplying a cosine by some other cosine gives something that has an average value of 0. But suppose k is equal to m. Let me edit that. If k is equal to m, then we have the sum from n equals 0 to n minus 1 of 2 pi kn times 2 pi kn. That will be equal to the sum from n equals 0 to n minus 1 of cosine squared of 2 pi kn, which will not be equal to 1, which will not be equal to 0. So what I've written at the bottom here is if I take the sum, if k is equal to m, then I have cosine 2 pi kn over capital N times the cosine of 2 pi kn over capital N. That's the sum of cosine squared, right? And if you square anything, you get a positive number. So we're adding up a whole bunch of positive numbers in the case only when k is equal to m. And so in that case, if I take x of n squared of n, add it up over n samples, then I get a non-zero value. So let's plot that as an example, right? If I take a cosine with a frequency of 3, and multiply it by another cosine with a frequency of 3, I get something where all of the values of that product are always non-zero, non-negative. They're always positive. And in fact, if you look at it more closely, you can see that when I multiply 1 times 1, I get 1. When I multiply a very small number, when I multiply 0 times 0, I get 0. And all of these samples are kind of uniformly distributed between 0 and 1. And so their average value is exactly 1/2, right? The average value here is exactly 1/2, which means that the total, when I add up all of these samples, the total is, well, let's see, there are 20 samples total, 0 up through sample number 19. And so the total is 1/2 of 20, which is 10. So when I add up all of those samples, I get the number of samples, which is 20, multiplied by 1/2. And so we have this sort of magic principle of orthogonality. The basis of the Fourier transform is this idea that if I have a cosine at frequency m, and I multiply it by a cosine at frequency k, and then add up all of the samples, that summation is equal to 0 if k is not equal to m, and it's equal to the number of samples divided by 2 if k is equal to m, right? So that's this sort of magical principle of orthogonality, that if I have a pure tone in my input, a pure sine wave, I can multiply it by another pure sine wave, and I get back 0 if those sine waves are at different frequencies, and I get 1/2 if those sine waves are at the same frequency. Now, why is that interesting? The reason that's interesting is because music is made up of pure tones. So suppose, for example, that we have a musical tone at the frequency omega naught, say that it's 440 hertz. It's a pure A, pure tone A. And then suppose that I multiply that by G cubed. G is 2 to the 1/12. So that brings it up 3 half steps, right? That makes a minor third chord. Right? G to the 4th is 4 half steps. So it's a major third. G cubed is 3 half steps, so it's a minor third. G to the 7th is what's called a major fifth tone, 7 semitones above the root. So let's play those. Let's start out at F0 is 440 hertz, and I'll have a sampling frequency of 8,000 samples per second. And then I'll create omega naught is 2 pi times F0 over Fs. That'll be the frequency of the bass note, the A note that it starts with. And little n will be the integers ranging from 0 to 2 seconds long. And then capital G is the amount that we multiply the frequency in order to raise it by 1/2 step on the piano. The major chord is the cosine at the frequency A plus the cosine at G to the 4th above that. So 1 major third up, plus the cosine 1 major fifth up. And if I play that major third, I get a note that sounds like the major chord, I get this note. Let's actually play each of those separately. Let's say the A note is equal to the cosine at omega naught. And let's say the major third is a C. So that's the cosine at omega naught times n. And I'll multiply that times G to the 4th power, G times G times G times G. And then finally, let's see, an A major chord is A, C, and E. So the E note will be the cosine of G to the 7th times omega naught times n. So that's 7 half steps up. And then the major chord will be the A note plus the C note plus the E note. All right, and first of all, let me just play the A note. There's the A. And now let me play the C note. And now let me play the E note. And now let's add them all together. So there we have a major chord. That's an A major. A major chord is just A note plus C note plus E note, where the A note is a cosine at the frequency 440 hertz. The C note is 4 half steps up, and the E note is 7 half steps up. All right. A minor chord is the same thing, but using a C flat, which is a B. So a B note is just 3 half steps up. So it should be cosine of G times G times G times omega naught times N. And then the minor chord should be the A plus the B plus the E. And then let's play the minor chord. So again, let me play each of those components separately. Here's the A note. Here's the B note. And here's the E note. And then let me play them all together. So you can hear that the chord that we get depends on exactly which notes are added together. We have a cosine at 440 hertz, a cosine that's up 4 half steps, and a cosine that's up 7 half steps. And when we play those, we get a major chord. But if instead of the one that's up 4 half steps, we substitute a cosine that's up 3 half steps, we get a minor chord instead. Right? So we have this wonderful music, right? Now we're making music. We're creating music by adding together pure tones, cosines, at 3 different frequencies. And what might be interesting is how do we get, suppose that we had that chord and we want to get it back again. If we plot it and look at it, we see, well, it's not at all obvious. What are those tones? Right now I'm plotting it just as a function of the sample number, but I could also plot it as a function of time. Let me plot it as a function of time in seconds. Let's see, the time in seconds should be, what should be the time axis? Time axis should be the same length as the same length as the note. So let's say a range of the length of the note. And that should be divided by the sampling frequency. That'll give us the time axis in seconds. And then let me just plot the time axis, the first capital N samples of the time axis, and then I'll give it a label. And let me also give it a title. Where the title will specify how many samples it is. There we go. Oh, that didn't work. Let's see, do I call it X label? I forget how I set the title. Nope, not X label, not title. Subfig dot set X label maybe. I may have to go look this up. Oh, there it is. It's set X label. Oh, let me set the font size larger. There we go. So you can see that the X label is in seconds now, 0.01, 0.02 seconds. And this is showing the minor chord. This is 400 samples from a minor chord. And I don't know about you, but I can't look at this and tell that there's one note at 440 hertz and another note at 512 hertz and another note 3 half steps up from that. I can't see those different frequencies just by looking at this tone. And so the question comes up, suppose you're given a voice, a singing voice, a beautiful singing voice, and you would like to resynthesize. How do you resynthesize it given just these samples? Like where did that come from? How do we understand what different pure tones are added together to create this tone? And the answer is the orthogonality principle. This magical principle that we discovered up here, where we we multiply together this cosine times this cosine, and we get something with an average of 0. That magical principle, summarized in this equation, this magical principle allows us to find out exactly which frequencies are in any given input. If we know that it contains a frequency at some frequency m, then we know that when we multiply some frequency k, the average will be 0 unless k is equal to m. And so in that way, we can pick up all of the same, figure out exactly which samples are there by using this formula. The average value of the cosine of 2 pi kn over capital N times cosine of 2 pi mn over capital N, that average value is a half unless k is equal to m, if k is equal to m. If k is equal to m, then the average value is a half. Otherwise, the average value is 0. And so we can do that by basically creating a matrix, right? We create a matrix where each row of this matrix is one of these pure tones. The first row will be a cosine at the frequency 0. The kth row will be the cosine at the frequency k. And the capital nth row will be a cosine at the frequency capital N minus 1. And we'll multiply this matrix times the input, and the output will be a whole bunch of zeros, except at the particular frequencies where we have some cosine in the input. So let's do that. We'll set capital N equals 20, and we'll create capital W is an n by n matrix. And the knth element will be the cosine of 2 pi times k times little n over capital N. So we'll go for k in the range of 0 up to capital N minus 1, for n in the range of 0 up to capital N minus 1. And wow, before I plot all of that, let me instead plot just what those frequencies are. So before I plot all of that, let me first plot something else. Let's say figure is equal to plot figure, fig size. Let's make it 8 by 8. And let's create subfigs. And let me create 4 different subfigures to show you the first 4 rows of this matrix. So let's say for k in range up to 4, we'll plot the first 4 rows of the matrix. In subfigs k, we will plot w of kth row. And let me set the layout tight here. I don't remember if that has to be in quotes or if that's layout or fig layout, so we'll find out, I guess. Subfigs k, set title. This is row number %d of the matrix W, where %d will be k. There we go. That should allow us to see all of the rows of the matrix. So we can see that row 0 of the matrix is all ones, right? Because it's a cosine at frequency 0. Row 1 of the matrix is a cosine that goes from +1 to -1 and back again. So it's a cosine that has exactly 1 full period. Row 2 is a cosine with 2 full periods, and row 3 is a cosine with 3 full periods, and so on. Let's plot one that plots all of the 20 rows. Let's see if we can do that and still see the contents. All right, here's all of the 20 rows of the matrix, and you can see that all of the 20 rows of the matrix, the frequency of the cosine gets higher and higher until the frequency starts to get lower and lower again. the frequency getting higher and higher is because we're going from a frequency of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Once we get past frequency 11, though, right, we don't have enough samples. So we get this aliasing that we talked about 2 weeks ago, where frequency 19 actually looks just exactly like frequency 1. So that's going to be interesting. That's going to mean that when we multiply by frequency 19, the result we get will look exactly like what we get by multiplying by frequency 1. Let's show that result. Let me comment out this figure, and instead I'll plot what happens when I multiply x, which is a cosine at some particular frequency. In this case, it's frequency 4. I multiply x by this matrix W, and I get as output some matrix capital X. And now what I'm going to do is I'm going to do a stem plot of that matrix capital X. And let's see what I find. I find that, lo and behold, multiplying this matrix W times this input signal, which is a cosine, gives me an output which is 0 everywhere except at sample number 4. So 0, 1, 2, 3, and sample number 4 is high, right? And this is exactly that orthogonality principle, right? When I take the average of a frequency 1 cosine multiplied by a frequency 4 cosine, I get nothing. But when I multiply a frequency 4 cosine times another frequency 4 cosine, I get 10, an average value of a half. Right, so that's exactly this formula. I multiply a frequency 4 cosine times a frequency 4 cosine, I get 10. Any other cosine gives me a 0, except for this one. The frequency is 16. 16 is 20 minus 4. And so this 16 is being aliased from the frequency 4. This is the same as that aliasing that we saw 2 weeks ago, where this frequency looks exactly the same as this frequency. And so they wind up with the same value. You can think of it as half of the energy went to this sample, and the other half of the energy went to this frequency. So we have the frequency 4, which is the true frequency of the cosine. Let me create two subplots after all. In subfig 0, I'll do a plot of the signal x, and I'll give it a title. And then in subfigs 1, I'll do a stem plot, and I'll show the title, which is the DCT, that shows that it has the information at frequency 4 and information again at frequency 8. So here we go. Here's the input, which is a time domain signal at frequency 4. 1, 2, 3, 4. It has 4 complete cosines in those 20 samples. And then here's the product of that W matrix times this cosine. So I have this cosine, input cosine, which is being multiplied by a cosine at frequency 0, 1, 2, 3. And when we get to frequency 4, we see a large product. All of the other products are 0. So in this way, we can take this input pure tone, and we can find out what is the frequency of that pure tone by just multiplying it times a matrix. This is called the discrete cosine transform. It's a transform because I'm taking something in the input, which is in the time domain, and I'm converting it to the frequency domain. And here I'm plotting it in the frequency domain. And so what I see is a plot as a function of frequency. What are the different frequencies that are that exist in this input? And this is particularly interesting if I take a much longer signal, like 400 samples, and create a 400 by 400 matrix W, and create exactly the same formula as before. W of k comma n is equal to the cosine of 2 times pi times k times little n over capital N. And then I'll take my minor chord and multiply it by capital W. And when I do that, I get the plot that's shown below. Here is the A note, the C note, and the E note, right? In fact, let me convert these into frequencies. Let me create a frequency axis here. Frequency axis is equal to np dot zeros of capital N, length capital N. And actually, no, it'll be np dot a range of length capital N. That'll be a number, that'll be numbers from 0 up to 400. And what is the sampling frequency for this A node? Was it, oh, it was Fs, right? So I wanted to multiply that times Fs and divide it by capital N, divide it by 400. So that means instead of going from 0 to capital N, it'll go from 0 to capital Fs, the sampling frequency. Let's see if that makes sense. That gives me, no, that doesn't, oh, I need to plot the frequency axis here. Now I think I'm going to be getting the answer in hertz. Let's see if that makes sense. So it says the frequency in hertz, this frequency is at about, well, it's a little bit less than 500, so about 440. This frequency is right about 500 hertz, so that's the C note, or the B note actually. And this frequency is right about 600 hertz. Actually, if I plot the major chord, I should have exactly a middle C in the middle. Let's take a look and see if that works. Yeah, here's the major chord. So this middle note here is at 512 hertz. And if I plot the minor chord, then I get the same, A and E will be the same, but instead of a C, I'll get a B in the middle. So here's the A and the E, but the middle note is a B. And you can see that these are about the right frequencies, 440, 500, and around 600 hertz. Actually, we want to kind of zoom in on those three notes. So let me zoom in on those. So I'll zoom in on just those three notes. Oh, I want to set the X label, set the axis from 0 to 1000 hertz. There we go. We can see that the A note is right at about 440. The B note is just right about 500 hertz. And the C note is up here at around 630 hertz or something like that. Maybe I can zoom in a little bit closer. Let's zoom in from, say, 400 to 700. That should allow us to see exactly what those frequencies are. We can see that this note is right at 440. This note looks like it's at around, well, let's see, that's 550, so this is it's about 520. And this note is at around 655. All right. Oh, let's look at it says here that we can see that the pure tones are at notes K equals 22, 25, and 33. So that means that I need to get rid of the frequency axis and just plot the sample indices. There are the sample indices, 20, 21, 22, 23, 24, 25, 26. Capital X is multiplying the minor chord, right? Multiplying with the minor chord. Let's make sure that I'm getting the minor chord here. Let's see, 22, 23, 24, 25, 26. Okay, so this should be sample number 26. And the last one is 30, 31, 32, 33. Yes, so those are at samples numbers 22, 26, and 33. And so the frequencies now, well, those frequencies are omega equals 2 pi f over fs, remember? We had f in cycles per second divided by fs in samples per second. So if we rewrite that, we see that little f is fs times k over n. Right, so fs is the number of samples per second, n is the number of samples in one period, K is the number of K is the number of samples per cycle, and F is the number of cycles per second then. All right, so we can take the little f and use that as the sample, as here's the frequency axis now is little f, which is k over n times fs. And when we plot that out, we see that these are at 440 hertz, 520 hertz, and about 655 hertz. So those are the A, the B, and the E note, the um, the uh, um, the notes of the minor chord. Well, actually, I've got written here that the minor third is A, C, and E. Does anybody know? I guess C sharp is the A major chord and C is the minor chord. That's what I have written in the lecture, that C natural is the minor third. All right, so what I've got so far is we've got the major chord is the sum of three pure tones, the minor chord is the sum of three pure tones, and we can get back again exactly what those tones are by multiplying by the corresponding cosine. We have almost everything we need in order to analyze real, natural audio signals. The only thing we don't have is sine waves. We have cosines, but we don't have sine waves. So what happens if the minor third is made up of sine waves instead of cosines? Let me make up a minor chord where I have the sine of omega naught n and the sine of the corresponding C note and the sine of the corresponding E note, and let me add those together and listen to it. There's the minor chord made up of sine waves. Let's go back and listen to the minor chord made up of cosines. The minor chord made up of cosines sounds exactly the same, right? I can't tell the difference between those. I don't know if you can tell the difference, but to me, those sound exactly the same. And the reason is that the human ear can't hear phase. I told you 2 weeks ago that we can't hear the difference between a sine wave and a cosine. The only difference is exactly when does it start, right? The sine wave starts a little bit earlier than the cosine. That's all. So will the W matrix be able to handle that? Let's create our W matrix with cosines, and let me multiply it times the minor chord, and then I'll multiply it by the sine wave minor chord. And then let me plot those two things. Let me plot the cosine, the cosine minor chord in blue and the sine minor chord in red. And what I discover is that the cosine minor chord is analyzed just fine by that W matrix, but the sine minor chord is not. Look, the A note has vanished entirely. The C note is just barely there, and the E note is just barely there. And so if the input happens to be cosines, then our W matrix is just fine. If the input happens to be sine waves, then our W matrix doesn't work. This is the reason why that was called a discrete cosine transform. Where did I put that? Let me go back to the beginning. I called that a discrete cosine transform. And that's because it only works for cosines. This discrete cosine transform only works if the input is the sum of cosines. It doesn't work if the input is the sum of sine waves. And so we have to solve that problem. And the way that Fourier solved it was by adding together cosines and sines. The problem is that to detect a sine wave, you need to use a sine wave. And so let's create our W matrix using only sine waves. Let's say that W of k comma n is the sine wave at 2 pi times little k times little n divided by capital N. We'll use sine waves instead of cosines. And what we discover when we do that, can I run this? Something's not working here. Let's see, what am I missing? My code has stopped working for some reason that I don't understand. Let's see, did this work? It seems to be. It stopped working. Well, I can show you the result because I had it calculated before, but I'll have to stop and restart at some point soon. But suppose we create a W matrix that's made up of sine waves rather than cosines. What we discover is that the sine minor chord is detected just fine, and the cosine minor chord is hardly detected at all. Again, the note at 440 hertz is not detected at all. The note at 512 hertz is detected a little bit, and the note at 655 a little bit, but hardly at all. And so if your input is made up of cosines, you need W to be composed of cosines. If your input is made up of sine waves, you need W to be made up of sine waves. Right? If W is made of cosines, then it can only analyze a minor chord made of cosines. If W is made of sines, then it can only analyze a minor chord made up of sine waves. And so Fourier's brilliant idea, what Fourier proposed is, all right, let's do both. We'll put the cosines into the real valued part, and we'll put the sine wave into the imaginary valued part. And he used this idea that you might have seen from high school algebra called imaginary numbers, right? We'll invent an imaginary number. J is the square root of -1. Right? We'll use this imaginary number j to mean the square root of -1. And we'll say that w of k comma n is equal to the cosine of 2 pi kn over capital N minus j times the sine of 2 pi kn over capital N. And that way, when we multiply wkn times x of n, if the input is a cosine at that frequency, we get a positive number. And if the input is a sine wave at that frequency, we get a positive imaginary number. And so whether it's real or imaginary, we still get some output. All right, how do we get back again some information about exactly where the tones are? We can take the real part and square it, plus the imaginary part and square it, and then take the square root. And this is what the function np dot absolute value does. It takes the square root of the real part squared plus the imaginary part squared and gives that back to us. So we need to create an imaginary number. J is equal to 0 plus 1j. That's how you write the number j in NumPy. It's a funny way. We could also write j is equal to np dot square root of -1. Let me test what I have written here first to see if this works. And then we'll take 400 samples. We'll create a 400 by 400 matrix, and we have to specify that it's going to be complex valued. If we don't specify that, then NumPy will not make it complex valued. It will try to make it real valued. Then we take the cosine of 2 pi kn over capital N minus j times the sine of 2 pi kn over capital N. When we multiply that times the minor chord, we get a positive real number. When we multiply that times the minor chord, we get positive imaginary numbers. And so if we plot the absolute values, those will both show up. Let me just plot. Oh, well, I've got them both plotted in separate plots here. So you see, if I multiply if I multiply times the cosine minor chord, I get positive real numbers. If I multiply times the sine minor chord, I also get large values. But these were originally imaginary values, and now I'm taking just their absolute value. All right, in order to run this code, I think it would be worthwhile for me to stop this notebook and try restarting in order to understand what's going on, because for some reason, Matplotlib has stopped working. So let me stop the kernel and then restart the Jupyter notebook in order to make sure that this code can actually be run. All right, let me just go through and run all the code in this notebook. All right, there's the first plot of the orthogonality principle. The average is 0. If they're at the same frequency, the average is not 0, because all the values are positive. And so since all the values are positive, we can use that in order to get back again the notes from the minor chord. Here's the minor chord, and we discovered that we can't really tell what's there. And so we detect all of its components by using the discrete cosine transform. Here's the discrete cosine transform. And here's the discrete cosine transform applied to that minor chord. We get back again the A, the C, and the E note. There's the A, C, and E note. And get them back again at 440, 512, and 655 hertz. All right. Now we have our sine minor chord, and then we multiply the sine minor chord times our cosine W matrix, and we get no response at all, or nothing very good. And so we try creating a W matrix with sine waves, and we get the opposite result. It works just fine for the sine minor chord, but it doesn't work for the cosine minor chord. And now let's take our complex valued W matrix with cosine minus j times the sine. And we discover here's the absolute value when we multiply times the cosine. Here it is for the sine. Let me plot each of these separately. Let me plot the real part of the x cosines and the imaginary part of the x cosines. And let's say these are the real part of the cosines and the imaginary part of the cosines. And so you can see if the input is the cosine major chord, then it's detected in the real part and not in the imaginary part. But now let me do x sines. This is where I multiplied W times the sine minor chord. So instead of x cosines, let me get x sines. And we'll discover that the real part of the sines is not detected, but the imaginary part of the sines is detected. So I'll correct the label. And here you can see that when the input is the sine minor chord, the imaginary part detects it rather than the real part. And here the real part detects very little, and only the imaginary part detects it. But in both cases, I can take the absolute value, and the absolute value will be large no matter what it is that I have at the input. Cosines are detected by absolute value. And sines will also be detected by the absolute value. So if I take the absolute value, then in both cases, I get a large output. It doesn't really matter anymore whether it's being detected by the real part or the imaginary part, right? The real part is the cosines, the imaginary part is the sines. In either case, we get a large output at 440 hertz, 512, and 655. And so we can see all of our tones. This kind of analysis is so important for music that it actually has a special function as part of NumPy. NumPy provides this function called FFT. Let's look that up. Let's go to NumPy FFT. And you can look up all of the information on the NumPy FFT package. It has several functions: FFT, IFFT, FFT2, FFTN. The one that you'll use most often is just numpy.fft.fft. And what this does is it takes the input, it assumes that the input is some audio signal, like a minor chord or a sine minor chord, and it creates an output, which is just our W matrix, our Fourier transform, multiplied times that input. And so when I plot the result, I'm going to plot the absolute value of the cosines and the absolute value of the sines. You see that it looks exactly the same as the result of our W matrix. In future lectures, instead of multiplying by a W matrix every single time in a future lecture, all of the future lectures will use np.fft.fft. The point of today's lecture has just been to show you what's behind the hood, in a sense. This package, FFT, takes the Fourier transform of an input and shows you which at which frequencies is there information in the input signal. But what I want you to do for today is to really just create this DFT matrix for yourself. So today's homework is just going to be to create a DFT matrix, W, which is of some size capital N. So W will be an n by n array of type complex, whose knth element is just the cosine of 2 pi kn over capital N minus j times the sine of 2 pi kn over capital N. So if we create a cosine with some arbitrary phase, say the phase of pi over 4, and then we multiply it times our W matrix, well, right now we'll get nothing because our W matrix has not yet been written. So let me go ahead and write that. Let's go to homework8.py. And here's that runtime error. We don't want that runtime error. We want instead to create a W matrix, which will be, let's say, zeros of size n, comma n, and it needs to be a data type complex. So let me create data type complex. And then let's say for k between 0 and capital N minus 1, for n in the range between 0 and capital N minus 1, we want W of k comma n to be the cosine of 2 times pi times k times little n over capital N minus j times the sine of 2 times pi times little k times little n over capital N. And then we just want to return capital W, right? There's two key things to notice here. One is that we need to make sure that it's of data type complex. And then the other is just the values. The values are the cosine of 2 pi times little k times little n over capital N minus j times the sine of 2 times pi times little k times little n over capital N. If I save this and go back here and multiply that W matrix times the input signal, I should get an output that has, all right, I need to reload it. Well, I still have an error. What's the error? NumPy has no attribute 0. Oh, I called it 0. I should have called it zeros. There we go. Here I used the function, I called the function name 0, and the function name should actually be zeros. Let's try that again. There we go. Here's the Fourier transform of cosine 6 pi n over 30 plus pi over 4, and you can see that it has non-zero energy at frequency 3 and also at frequency 30 minus 3. And here it is computed with the FFT, NumPy FFT, FFT, and here it is computed with the W matrix that we created in this week's homework. If you've done that and then you run the grading function, you should get all of the tests passed. And so at that point, it's time for us to run GitHub Desktop and try checking it in. Let me see if that works. Let's see, homework 8. I did homework 8. And let me commit those 3 files. And now let me push that to the origin. And now if that worked all right, then we should be able to go to GitHub and see the result. I'm not sure if I'm logged into my teacher account today or my student account. Looks like I'm logged into the teacher account. So let me try changing to the student account. All right, here I am logged into my student account. If I go to Intro Speech Understanding 2025 Spring, Lecture 8, homework8.py, and there it is. It's all there. And so I should be able to copy that URL and go to homework 8. There we go. And it says enter the URL of your copy of Homework 8. So go ahead and enter the URL of your homework here, and then I'll go through and check them and give you 10 points. And that's how that will be. Let's do attendance. All right. I'm going to log in for attendance here. There we go. All right, it's running a little bit slow today. That's probably a network problem on my end. I think it's opening attendance. Goodness, we're slow today. Here we are. Oh, I've forgotten to go on that button or this button. Nope, that's not it. Here we go. All right, please go ahead and register attendance using the code 19922. I think we have 10 of you online, so all good. Five already registered. The other 5 of you, please go ahead and register your attendance. That's 9 already. Is there one more? All right. Thanks, everyone. Have a good week. I'll see you next week. Take care.
Thank you, Sensei.
Thank you. Bye-bye.